Hey, welcome everyone. Mark here at Blue Glow Electronics. Today we're bringing you part 3 in our Oscilloscopes for Audio 101 series. We have gotten great feedback on parts 1 and 2 thus far, so super excited today to get to bring you part 3 in this series. Hopefully for part 4 and 5 will come just around the corner here in the next few weeks. And oh yeah, by the way, this today marks our 300th YouTube video that we will be posting, so take a minute and celebrate a little bit with us. But let's dive on in. All right, here's the series we've got going. If you haven't watched parts 1 and 2, I'd highly recommend you go back and do that. Some really good foundational stuff there. Part 3 we're going to cover today, just the basics of an oscilloscope and how to use one, okay? It's kind of like, remember the first time you ever got behind the wheel of a car and all these gauges and dials and knobs and shifters and whatnot, and it's intimidating, right? But now you go out, jump in your car, back out the driveway, you don't even think twice about it, and you probably don't even look at half those gauges or dials. An oscilloscope's no different. It's got a lot of knobs, bells, and whistles, but you probably don't use 2/3 of them, and the ones you do use, you probably don't adjust all that much. So we'll show you that today. Next week, I'm wanting to just get on the bench with both a digital oscilloscope and an older analog scope and just do a bunch of testing. Get you guys' head kind of where my head's at and use the logical steps of an oscilloscope to try to solve problems inside of audio gear. And then part 5, which is what I really wanted to make to begin with, but everybody talked me into making parts 1 through 4 first here. I want to show you how to use an oscilloscope to analyze your audio quality and your audio signals. So stay tuned for those. Let's dive on into part 3 today. All right, let's dissect the most basic definition here of an oscilloscope. It says it's a type of electronic test instrument, in other words, a box that you can use to measure things with, okay, that graphically displays varying signal voltages. In other words, it's designed to look at AC waveforms, okay? You can measure DC with an oscilloscope, but it's kind of boring, and honestly, a digital multimeter does just as good, if not a better job of doing that, okay? So we're going to be looking at these varying signal voltages, usually as a calibrated two-dimensional plot. Don't let that scare you. We're just basically looking on a screen at one or more signals as a function of time. So in other words, we've got this AC waveform, in other words, a varying voltage, and it's varying over time, right? And you can see here this little green line that we've drawn, right? It's a sinusoidal waveform, and it's going up, back down, back up, and that thing does that repeatedly over a given time interval, right? And it says here then, the displayed waveform can be analyzed for properties such as amplitude, okay? What's the height of this voltage? How much does it go up in voltage? How much does it go down in voltage? What is that amplitude? Okay, frequency. How often does this thing happen, okay? How often does it repeat? Does it happen once a second? Does it happen once every minute? Once every microsecond? Things of that nature. We can look at rise time, the amount of time it takes to go from 0 to its peak, right? Time interval, right? What is the length of the waveform, right? Distortion and other factors. And you can see here on this little chart, usually on the x-axis, we mark time. So how long does it take for this signal to do its thing and come back and start over again, okay? And on the y-axis here, we're looking at the magnitude of it, right? So how big is this waveform? All right, when you have a varying waveform that repeats itself over and over and over, and that's what we typically measure with an oscilloscope, okay? And this just happens to be a green sinusoidal waveform here that's repeating itself. You can pick any 2 points in a signal that happens once in the waveform, but then happens again when that waveform repeats itself, and you can measure the distance between those two in seconds. How long did it take from the time it happened once till the signal repeated itself and it happened again? And you measure that in seconds. That is known as the period of the waveform, okay? When we're talking about audio work, typically the period is measured in milliseconds, sometimes microseconds, okay? But what you don't find, us engineers, technicians and audio geeks, we don't run around talking in terms of time and period. You don't hear someone say, oh, the frequency of my signal takes 12 microseconds to repeat itself, right? That's a lot to say. It's just not what we do. What we do is we talk in terms of frequency, okay? And frequency is a super simple math equation. It is the number 1 divided by the period in seconds, okay? So let's do an example here. Let's say this signal repeats itself, right, in 16.666 milliseconds. Now, a millisecond is 1,000th of a second, so every 16.666 milliseconds this thing repeats itself. Let's do the math then. 1 divided by 16.666 equals 60. We then talk about this in terms of its frequency as this is a 60, and the unit of measurement for frequency is hertz, okay? So we then say this is a 60 hertz signal, which means it happens 60 times a second, or once every 16.666 milliseconds, okay? If you can grasp that, you're like 9/10 of the way through using an oscilloscope already, and you may not even know it. I thought we'd just do a quick little history lesson for a minute here. Back in the day, we had analog-based CRT, cathode ray tube-based oscilloscopes. They work great. They're all you ever need for audio work, to be honest. But a little bit of downside to them in that the waveform displayed on this, you're going to have to actually count these little gradients here and count your waveform yourself, and you're going to have to do some math yourself. So if you wanted to figure out the frequency of your waveform, you'd have to count left to right in terms of seconds, right? Milliseconds, and then you'd have to do the math yourself over here on a calculator and say 1 divided by what I came up with. That's what the frequency is. So nothing wrong with that. It's doable. But what happened next was oscilloscopes evolved a little bit, and they were still analog CRT based, a little bit nicer, cleaner screens. But what happened was they started adding digital measurements displayed on the screen as well. So you can see these 4 waveforms being displayed here. By the way, this is the 2246 on the bench behind me here. You can start to see here the waveforms being displayed, and you can see here this is 0.5 volts, 0.5 volts, 0.5 volts, 0.5 volts. And oh yeah, by the way, at 20 microseconds. So it's giving you that frequency and time displayed on the screen right there, okay? Beyond that, what happened was a further evolution, and these two kind of happened at the same time or similar time frames, to be honest. You got the digital display, but a lot of oscilloscopes had these little modules built on top of them here that were considered digital storage. So they also had some RAM, so you could take a snapshot of a waveform and save it for later and maybe compare that waveform to another waveform, right? So it was starting to let you capture things over time, which can be handy for certain uses. I don't use it that much when I'm doing audio work. And then finally, the modern digital LCD-based oscilloscopes that, by the way, do all of these things. They do the on-screen display. They can capture waveforms and play them back to you, things of that nature, okay? So it doesn't matter which of these you pick, you can still do audio work. Some of the ones over here on the right just make things a little simpler and keep you from having to calculate stuff on your own. Remember earlier I talked about this repeating frequency or repeating waveform? So that can hold true regardless of the shape of the waveform, okay? So a sinusoidal waveform repeats itself and we can measure that. A square wave repeats itself in terms of a series of pulses almost. This little triangle waveform here, this little bit of trapezoid waveform. Or over here on the right, this is an audio signal, okay? But if you'll notice, maybe there's a beat in the background to this audio signal, right? Boom, it happened here. Boom, it happened here. Boom, it happened here. Boom, it happened here. And so that beat behind the scenes may be the repeating part of an audio waveform here. And so that'll become important as we talk about how to trigger on a waveform here in a little bit. All right, finally on the bench, but I want to orient you a little bit so as I dive into the oscilloscope, you understand what I've got going on. So up top here, I've got a function generator. Nothing special about it. It has a couple features to it that a lot of function generators have. One here, it will let you change the type of waveform. So a little bit of a triangle wave there, sine wave, square wave. We can play with different things here, okay? We're going to leave it on the sine wave for most of the part, but this may be one button that I vary, and if I do, I'll tell you I'm changing the shape of the waveform. The next thing it will do, this knob right here, it allows me to adjust the frequency. Now remember earlier, two axes here, right? The x-axis that we're going to talk about in terms of time or frequency, and the y-axis we're going to talk about in terms of voltage amplitude, okay? So as we vary this, you'll notice what's happening down here to this waveform. It's changing, right? And it's changing on the time axis, okay? So that's a 4.3 kilohertz signal. So in other words, 4,300 times a second, this waveform is repeating itself. And I'm going to roll it down here to roughly a 1 kilohertz, okay? So 1,000 times a second, this signal is repeating itself. And when I say repeat itself, it's from this peak to this peak. Here to here is only half of a repeating signal. It's got to completely come back to the same point. Now I could measure from the bottom to the bottom. That's the same as measuring the top to the top. I could also measure where it crosses the 0 point here and the 0 point here in the middle. And that would help me understand how long that waveform takes to repeat, and we could read that out in frequency. Happens to be happening 1,000 times a second. So I will be adjusting this little knob here, and when I do, I'll tell you I'll be adjusting the frequency, and we'll see it going this way. Next knob here that we need to concern ourselves with is the amplitude. So watch what happens when I turn it, okay? The signal gets bigger. In other words, more volts peak to peak, so the signal gets bigger. Less volts peak to peak, the signal gets smaller, okay? So if I talk about varying the amplitude, that's what I'll be doing, and we see that increasing or decreasing here on the y-axis. That's really all I'll be doing with this unit today. So frequency, shape, and or amplitude. Let's get zoomed in on the oscilloscope itself. One more quick thing, all I'm doing is coming out of the main here, the main output, and it's just a BNC connector that I've plugged a BNC cord into, a piece of coax cable. I'm coming down here, I'm feeding into a little T connector here so that I can feed into channel 1. I'm coming out the other side of that T connector with just a single black cord here, as you can see, that does nothing but go from here to here. That way I've got the same signal feeding in on both channels of this oscilloscope. And as you can see, if I wanted to measure what's happening in channel 1 and 2, I could do that. So just a simple coax connection here that I've wired up. Alright, Textronics does a pretty good job here, and I apologize for the noise in the background. Both these units do have fans, and there's nothing I can do to get rid of the fan noise, but Textronics and most oscilloscope makers do a good job of kind of grouping things together for you. So this whole section right here is about the on-screen display and how your waveform might show up, okay? Along with this little thing here called a power button. Push it in to turn it on, push it in again to turn it off. Right here grouped together, we've got some functions around some on-screen displays. We've got our vertical section of the oscilloscope. We've got our horizontal section of the oscilloscope. We've got over here our triggering functions, and that's really all it is. So to break it down, it's pretty simple, and we're going to walk you through each and every one of these sections here today. So let's start down here, okay? If you can't figure out how to operate the power button, you probably shouldn't be watching my video series here, and I'm just playing with you a little bit. But here we have something called A intensity, okay? I want you to watch what happens when I turn this. My trace goes away, my beam, okay? Or it gets super, super bright till it's blinding me here in the room, okay? And I see people that run their oscilloscopes like this, super bright. I even see it in some YouTube videos. It's not such a great thing, because what's happening is you're hitting the beam on the back of this phosphorus screen really hard, and over time you're going to wear out the phosphorus on this more likely than if you run it down here, something like this. So what I do is I run mine just bright enough that I can see everything clearly, but not bright enough that it's starting to blur or blind me there. So, and I'll tell you, I've been using this oscilloscope here for probably a good 15 years or more, and I've not had any problems burning up the phosphorus here. There's also a knob here called B intensity, and it's for a time delayed signal. You can do a zoom in function and look at little pieces of this signal. I'm not going to be showing that as part of this audio or oscilloscope for audios series, but that would let you adjust the intensity on that zoom in function. Okay. Up next here, we've got the focus button. Notice what happens when I turn it to the right. Trace gets really blurry. Notice what happens when I turn it to the left. Trace gets even blurrier here. It's just the screen focus. Remember on TVs years ago, you used to have to turn the little focus button. So you just turn it kind of the null between both sides of blurry till it's the absolute sharpest, and you leave it alone. Okay, up next we have something here titled readout. Now, this oscilloscope happens to have a readout that shows you what the settings are for the horizontal and the vertical. So what this is telling me that each of these little gradients right here, this is 0.2 volts, okay, per little box. Okay, so if I looked at this signal, I would say 1, 2 boxes going this direction, 1, 2 boxes coming down. So that signal total would be 0.2 times 4, or 0.8 volts peak to peak here. Now, I can do that math myself. On an older oscilloscope that doesn't have these little displays down here to tell me, you actually have to come over here and read it on the dial itself. So you just read on the dial and it would say 0.2 volts per division, right? But this one just happens to display it on the screen. Same here with the milliseconds. It shows the time base. So if I change the time base, I'm changing that. If I change the volts per division, I'm changing the readout on it. I never varied the signal. I'm zooming in and zooming out on that signal via more or less volts per division and more or less time on the other axis, okay? So what this readout knob is it is the intensity of that little readout. If you notice, I got it super bright, or I can make it completely go away there. There again, I just put it bright enough that I can read it and no more, and leave it like that, okay? And last here, you've got something called scale illumination, okay? This little oscilloscope, I leave mine down all the time. I don't use it, but you can turn it up to the point that it illuminates the little lines on the scale here, and you can actually see those, and you can see here it's outlined and it's kind of orange behind the screen at this point in time. It's just something I can see my if you're working at night and couldn't see the scale or something with the dark in the room, maybe you want to illuminate it. But okay, the next little section we're going to talk about today is the vertical section. And when it talks about vertical, guess what that means? This axis over here, right? On the y-axis, okay? So right now I've got it set on channel 1. There's a little section of buttons here, and I've just got it on channel 1, which means I'm only reading on channel 1 of this oscilloscope. By the way, this is a 4-channel oscilloscope. I keep these that I don't use often kind of covered up, and you'll notice there's dust on top of that. What that tells you is I do a lot of audio work and I only use 2 channels. So if you're thinking you need a 4-channel oscilloscope to do audio work, probably not. It's a hint. Good 2-channel scope will do everything you need, okay? So with that, got this little knob here that I turn, and guess what? I vary the volts per division. Now notice, I have not changed my signal at all. I did not change the function generator. So my signal has not gotten smaller, just the volts per division. Now I'm at 0.5 volts per division. So each of these little blocks here is 0.5 volts. I can take it on down to 1 volt per block, okay? Remember earlier I said this was a what? 0.8 volt peak to peak signal. So if I move this up till it's sitting on the middle line, it would take me up to just below the next little line there, and I would be seeing that I have a 0.8 volt signal there, okay? Now you notice something I showed you. I showed you the position. This is arbitrary. You can put it wherever you want, right? If you put it dead in the middle, then you could kind of know that is the center line of your signal here. And by the way, it's kind of hard to work with a signal like that, right? I like to get my signal on up there, so I'm using a lot of the screen here. You don't want to get it too far, though, that you're starting to go off screen, top and bottom. So something like that right there might be a good place to be at, okay? So I'm varying my measurement here, not the signal, the same exact signal in both of these scenarios, okay? Now, if you'll notice here, I've got channel 1, I've also got a channel 2 button. I'm going to push the channel 2 button. So what I've got going on now is I have channel 1 and channel 2 both going on this screen, and this little set of knobs right here controls channel 2. So I can have channel 2 on a different voltage base, okay? 0.5 volts per little section, right, versus the 0.2 volts, okay? It just flattens my signal out. I also have a position knob here that I can use to move the channel 2 up and down. So I got position for channel 1, position for channel 2 here. And then there's a button here in the middle that lets you add these two signals together, and it shows you a third waveform that is the sum of those two waveforms added together. There are times you might need to use that, maybe not so much for audio work, okay? So let's just take it back to a single waveform. So this little piece here in the middle, little knob, it says VAR on it. It's a variable. So if you'll notice here, I've got 0.2 volts. Here I've got 0.1 volts. Here I've got 0.5 volts. What if I wanted 0.3 volts per division, right? Well, that's what this little variable does. It lets you vary somewhere between the other two settings. And what does it tell you? It's greater than 0.5, but it doesn't give you the exact readout. I'll tell you, I use that function almost never in doing audio work. I can almost always measure what I'm wanting to measure somewhere on screen just by varying the divisions that it gives me. Okay, let's take a look here. So we've covered these buttons, and by the way, if you turn channel 2 on and turn channel 1 off, now I'm seeing what I'm feeding into channel 2. It's the exact same signal I'm feeding in here as I'm feeding in right here. Right? Let's do this. Let's put it on channel 3. Interesting. What do we have? We have a flat line. Okay, that is 0 volts. In other words, we just have a signal going in. There is no varying amplitude because it's right here. There's nothing plugged into it at all, right? But one thing to notice about channels 3, 4, and 2, they all share the same time base, okay? So if I turn channel 2 on, and I've got 3 channels going. If I turn channel 4 on, I've got 4 channels going. And by the way, you can use different position knobs here to put the different channels where you want them. Like you could put one down here. Maybe you put one up here. You can just put them on the screen where you want them to be able to look and see at different things. But what I was just showing you here, let's just say we only show channel 3 here. That's what a DC signal looks like. So if you're looking at 0 volts DC, it looks like that. If I was to crank up the voltage and have at 0.5 volts, let's say I had 1 volt signal, all I would have is a line straight across 2 bars up from that. It's pretty boring, to be honest, and that's why you don't use an oscilloscope a lot to measure a DC signal. Okay, so you kind of get this controls channel 1, this controls channel 2, and you're like, well, channel 3 and 4 over here, if you'll notice, they share controls with this. And so one time base for all, and then channels 3 and 4 start to share the voltage base with channels 1 and 2. So that's why I don't use them that often. They're not that super effective, if that makes sense. All right. So we've shown you here with 2 channels, we can vary positions of each of those. We've shown you we can turn signals on and off. We've shown you we can add between them. Okay, coupling, here we go. Hang on one second. All right, here we go, coupling. What that is when you feed your signal into your oscilloscope right here, okay? And it's an AC waveform feeding in, but sometimes your AC waveform is riding on top of DC. In other words, it's not biased around 0 volts. Maybe it's a 5 volt DC signal with a 1 volt peak-to-peak signal riding on top of it, which would mean it's going from 5 volts up to 6 volts, back down to 5 volts, down to 4 volts, and back up, okay? You can see that here, but if I happen to put this unit on DC, and let's just say I applied some DC voltage to my signal. Did you notice what happened? My signal rose up by the amount of DC that I applied to this signal. Okay, well that's good and grand. You can see, hey, my signal is riding on top of some DC component and it's moved up because of that. Well, what if your DC signal that it's riding on top of happens to be 200 volts? Woo! You just lost your signal and you're not going to find it. It's going to be way up there, okay? So you can switch this unit over to what's called AC coupling, and all it does is put a coupling capacitor in line with this signal, and it removes the DC component. Watch this. Let me put it back on this. Watch, I'm going to move it up here, okay? So it's starting to go offline because I've got this DC component added to my AC signal. Watch what happens when I AC couple it. Brings it right back down, and then I can use the position if I want to hover it around the 0 mark there, okay? You're just removing the DC component of the signal feeding into this oscilloscope. Okay, by the way, I almost always leave this unit on AC coupling on both of these for audio work, just for whatever that's worth. Okay, there's a little, while we're over this way, there's a little box here called Calibrator. And what that is you can use it to calibrate your scope probes. Okay, if you'll notice, your scope probes have a little calibration thing right here. What you do is you plug your oscilloscope in, let's put it on channel 2 and take it off of channel 1. And then you just clip your probe onto this little signal here, and if you'll notice then, it'll tell you that it is a 1 kilohertz signal at 0.5 volts. Okay, and if you'll notice here, I've got this little swoop up on my signal. I could use a little bitty screwdriver to adjust this scope probe right here. It's just a little trimmer capacitor inside of there, and you would get that signal as flat as could be. And what you're really doing is calibrating your scope because it's putting out a known signal right there. That's what it's used for. Okay, while we're over on this side, there's also a little button here called Beam Find, and I'm going to show you how to use that. A couple things, one more button I need to show you. I've been showing you can do the position of your signal this way, up or down. There's also a button here that does position, and by the way, this works for all 4 channels. You can kind of slide your signal off to the left or off to the right. So let's say you were wanting to count from the beginning of this little signal right here. You might move it all the way to the peak, you might move it all the way to the left there till it touches the very edge of your screen, and then you could say 1, 2, 3, 4, 5, or almost 5, and you could count that way. So that's the reason for the vertical position. Well, let's do something here. I put it back on DC coupling. Let's add a little bit of, let's just say you clipped on with your oscilloscope probe, and boom, you don't see anything on your screen anymore, but yet you know there's a signal there, okay? You can use this Beam Find button, and look what it shows you. See that the line at the top? It's telling you that that signal is going off the screen upwards, right? So I can then grab my position button and start scrolling it back down, and then you can kind of see it come back into focus here, and you'll see it's back online here, okay? Now, what if it was out the bottom, okay? Well, let me take it down this way with some DC offset negative, okay? There we go. This line down here is brighter than that line. It's showing you it's off the bottom. You would know to turn your signal upwards to get it to where you want to need it. Okay, let's say it's off the screen to the right too far. You can see here, it'll give you an indicator that it's scrolled off to the right, or it'll give you an indicator it's scrolled off to the left. So it's just a way of finding your beam. If it happens to, you happen to hook up to something and boom, like, whoa, where's it at? I don't know how to find it. Do I adjust this? Do I adjust that? What do you do? Beam Finder will tell you exactly, hey, that thing's up top. I need to bring it back down and find a home for it here. All right, check this out. We've already learned this whole section, these two. We've learned the whole vertical section here. Let's get over here into the horizontal section, okay? Horizontal is just that. It's the x-axis, and we're starting to play with time, right? So if you'll notice, 1 millisecond per little division, okay, and I can shift this using the position button, kind of get it right there on the peak of 1, and you'll notice 1 millisecond between these divisions. And because I'm on a 1 kilohertz signal here, to go from the bottom up all the way back down, right? Or if you started in the middle, up, down, back to the same point, either way, it's 1 millisecond in between those. I can and I can make it really, really tight between these. I can stretch it way out and kind of zoom in on this thing. You know, that's a practical level right there for measuring an audio signal. Okay, you've got something here called 10x magnification if you want. You can zoom in on that thing. Gives you a 10x going this way. Now, 10x going horizontally, you typically pick that up via a little switch on your probe here to go from 1x to 10x. But if you want to go 10x this axis, it actually gives you a button here on the oscilloscope to give you a 10x function back and forth. Okay, up next, you've got, say you've got two signals going on, channel 1 and channel 2 here. Okay, there's a little mode selector here that you can go. So on the time division, you can go A, you can go B, you can kind of alternate between them, or you can go X, Y, and I'm not going to show you that today. Really, most 90% of the time you're going to leave it on A. In video 5, we will use the XY mode, and I'll talk about that. But both these buttons here do nothing more than move up and down in between those. This little light here will come on to indicate that you're on variable, and that you're, so like what happens if you accidentally hit that little button and you didn't notice it, right? So you're over here playing with things, and you're like, God, things don't seem right. This little light just tells you that you're on variable. In other words, you're not locked in on a calibration. The same here. If you'd happen to bump that and get it off, this little light comes on here to tell you that you're not locked into a specific voltage there per division. Okay, and remember earlier I told you that that you could do this little time delay thing I had mentioned. Well, that's here where you're starting to zoom in on part of the signal and see parts of it or whatnot. But there again, not going to get into that in this video segment. And that trace separation is tied into when you're doing some of those types of functions. So in reality then, all you have left on the horizontal side here is the position of channel 3, the position of channel 4, the volts per division kind of markers here that they have for each of those channels. That's really it as far as it goes as vertical and horizontal. This right here, we'll talk more about it here in a little bit, and then position, as we talked about earlier, was kind of left, right on your signal. So up next, let's talk about triggering. So what is this triggering thing we speak of? Okay, you notice we got a nice clean sine wave right here, okay? And a sine wave is really easy to do what we call trigger on. Not all signals though are sine waves, and not all signals are nice and clean like this, so some are more difficult to trigger on. And this whole section up here in green is dedicating to triggering. And you say, well, what the heck is triggering? Well, let me give you an example, okay? This is an untriggered signal, okay? In other words, it's not locked on to that sine wave, okay? The oscilloscope's time base has to get in sync with the signal's sine base. Otherwise, your signal is constantly scrolling one direction or another and not locked in. And so it doesn't show your repeating sine wave over and over and over. Well, when you have something like this, a repeating sine wave, and yes, my drawing is horrific, you typically pick a spot on this sine wave, and let's just say it's this spot right here on the upswing, so the slope going this direction, okay? And you want to lock in on it. So you would lock in it there, you would lock in on it again here because you're on the upswing. You would lock in on it again here, the upswing, and it uses these little upswing measurements to say, hey, based on that, this is a repeating signal, and we are going to hold that signal steady on the screen. That's what triggering is. Now, if you'll notice this little button here, it says when it's lit up, it's triggering on the upswing, okay? I could change this over to trigger on the downswing. So in other words, I would be triggering when the signal is going downwards, and I could pick a place here on the downward slope where I'm going to trigger each and every time, and it would hold this signal true to that, okay? I could trigger on the peaks up here. I could trigger on the very bottom of these signals, and let me show you why you might not want to do that. So what if your signal repeated every certain time base, but the amplitude was different every time it repeated? Say the amplitude was higher every other time. Well, if I triggered on the upswing way up here, guess what? I'm going to be triggering on a signal that is this time base and not this time base. And what I may end up with then is, much like I showed earlier, something that is scrolling like this and not locked on to every single sine wave that's taking place. Okay? Now, what happens if I've got a signal that this big signal here happens, let's just say once every 10 microseconds or milliseconds, whatever, but these little things here, the little ripple or modulation that's taking place on the peaks, happens at a much faster frequency. So maybe this is 1 kilohertz and this is happening at 5 kilohertz or 5 megahertz, something else. If I triggered on the upswing right here, I would also pick up this and this and this and this, and my time base wouldn't be based upon what I'm wanting it to be based upon. And watch this signal. Instead, it would be based upon here, 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 here. And what would I end up with yet again? I would end up with some kind of signal doing something like that. So you're wanting to pick the waveform that you're wanting to trigger on, and what that does, you've got a knob here that's called level, okay? And with the level, you're basically adjusting where on the upswing, if that's what if you've got it illuminated there, you're adjusting. See, notice how I got it swinging off? So that trigger determines the level of where you slope. Then there's this thing here called hold off, and that determines the time from when you pick a spot until it tries to find that spot again on the scope. And let me give you an example here. So here, this one, I can use the hold out to try to get it to lock on, but it's odd. I never can totally get it to lock on. And you may wonder, well, why can't you ever get it to lock on here, Mark? Well, this little whole section right here is based on what do you want to trigger on. Well, if I put it up here, I'm triggering on vertical on channel 1. In other words, whatever this setting is on is what I'm triggering to. If it's on 1 volt here, I'm triggering based upon whatever settings are on this stuff. If I go down to just channel 1, then I have to pick the level of what I'm triggering on along this way. If I go to channel 2, right, the other channel, remember I'm feeding the same signal into it, so it happens to trigger the same. But I'm triggering on channel 3. Well, guess what? There's no input into channel 3, so I have no idea what it's triggering on right now, and you can never lock in because of that. The same with channel 4 here, okay? But if I get it back on channel 1, when you have a sine wave, most of these scopes, like right now I've got it on auto level, it'll find a level and it'll lock on it. This auto sensing piece, it's pretty darn smart, and it'll lock on just about every time. Here's the good news about all these little buttons and knobs over here. So this here, auto, then you can go down to auto level, auto, what is that, runs after. This is normal. Normal ties back to what's on this. Then you've got line, so 60 hertz, it's locking on that. You've got something here called TV field, and then you can go external, which is on the back of the scope here, another BNC input that you could sync to a time base of, okay? So you kind of got what do you want to sync to, or how do you want to sync? Then you've got what do you want to sync to over here. And then this is just another, you can say, hey, let me look only at the AC signal. This would say, let me look at the AC signal plus the DC. This would cut out any noise. This just puts some filters in line. This would cut out some high frequency noise that may be getting in your way, some low frequency noise and whatnot. So at any rate, I typically leave mine on noise over here. I typically leave this triggered on channel 1, and I typically leave this up here triggered totally on auto. The good news is I don't have to touch this 90% of the time when I'm dealing with an audio sine wave. Now, if I'm actually looking at a real audio wave, which is made up of a lot of frequencies all at one point in time, I may need to play with these trigger things. The good news is these are the only two knobs. You really just have to adjust one and or the other until you get locked on trigger wise. You can't go wrong here. You can try everything over here, right? So if, let's say your signal's scrolling, you can't get it to lock on, and you're playing over here with different time bases and different levels, and you can't ever get this thing to lock on. There's nothing you can do here that will harm the oscilloscope. Just play around until you get it to lock on. So you don't have to be a scientific expert at this. You can be a little bit of an experimenter and just play around until you get your signal locked on. Good news is most of our audio testing, we're going to be playing around with sine waves, or we'll be playing around with square waves. And with both of those, it's really easy to lock onto either this up scope or down scope or one of the peaks here. And if you put it in auto, it'll pretty much find it for you and make life really simple. Okay? So triggering 101, not a lot to it after all. If we were dealing with much more complex waveforms, let's say we were dealing with a TV signal. So you've got an audio subcarrier built in there that's at, somewhere between maybe 10 hertz up to 20 kilohertz, and then you've got that being modulated onto some high frequency up in the hundreds of megahertz range, and you're trying to take a look at that, it can get pretty complex. Or if you're trying to look at digital signals, but for remember, this is oscilloscopes for audio 101. Triggering's a pretty simple thing for us. Okay. So we have pretty much covered the vertical now, the horizontal, okay, how to trigger. Keep in mind these two little things here are just tied to the position of channel 3 and channel 4 up and down. You do have a little volts per division. You can either set it here on what would be 0.5 volts or 0.1 volts on channel 3 or 4. And if you need to use channel 3 or 4, just read your manual on what those mean. I'm not going to get into it, but it's fairly simple. Really all that's left is this little section here that kind of comes up and goes down along the screens here. And this is measurements. Okay, so what you can do here is you can turn this unit here, you can put it on volt. So it's actually got a digital multimeter built into it, kind of. And I always use peak to peak here, so I'll push this button. These buttons here correspond to what's on the screen. So when I push that, if you'll notice now, I've got a line going across at the top and the bottom, and it's measuring the peak to peak waveform of this. And it's telling me here in a readout on the top, I've got 1.16 volts from peak to peak. And it'll tell you here, what's it reading? Channel 1 peak to peak, okay? If you'll notice, as I vary the amplitude, what happens? Those lines redraw. Now I'm measuring the 0.64 volt signal here on the input, right? It takes just a second, but it'll change with you, okay? Up next here, you can do a time measurement, okay? And if you'll remember, time would be how long does it take this signal to maybe go from this point right here to this point right here. So I could push this button here for seconds, and this is where these two knobs right here come into play. The one on the left will adjust over here, and you get it in the middle of your peak right here. And then the one on the right will measure the distance between, and then you kind of get it on the next peak over here. And what is it telling you right here? 270.4 microseconds in between these two lines. What did I say earlier? Us self-proclaimed engineers, techs, audio geeks, we don't talk in terms of time. We like to talk in terms of frequency. So push this time button again. Then it'll do 1 seconds, which is, what did we say earlier? It's frequency. What is it telling me? We have a 3.698 kilohertz signal from that point to that point. And if I looked up here at the top, I've got 3.683 on my meter up here. And you say, well, why is one 3.698 and one 3.683? Here's the reality. I probably don't have this thing exactly on the frequency, and if I get it exactly on both sides. Alright, now I've got 3.68 kilohertz, and up top I've got 3.68 kilohertz. We're spot on at that point. So, you know, a little bit of variation there as you know, very, very touchy controls, and but you get in the ballpark. The reality is you got a 3.68 kilohertz signal there, okay? This little button here just kind of clears the screen of that. All these buttons are tied to what pops up on top, and I'm not going to get into these other buttons because you don't use them that often, but hey, the manual will tell you what they do if you want to dive deeper. But for our purposes, you have kind of seen what this oscilloscope needs to do. Guess what? We have just walked through all the crazy buttons and knobs on this oscilloscope and showed you everything that they do. Let's do this. Let's unplug this unit, and we're going to finish off our glass of wine here along with it, and we're going to get out a digital oscilloscope and show you the difference. One of the major differences you're going to see right out of the bat, whoops, this little whole section right here that's kind of tied to how a cathode ray tube works will not be there for a digital oscilloscope. So it makes it even easier. You don't have to worry about all this stuff. Okay, here we are. This is my Rigel 1054 DS1054. I paid about 300 bucks for this probably 4 years ago. Great little oscilloscope. There's newer models out now. There's also the ten-tec. There's other really nice oscilloscopes in this $300 to $350 range. And for audio work, this will do all you ever need and then some. Look, it's very similar to what we had before. We've got here, right, our channel 1. We've got a position knob here. Look at this. When we change this, we're changing the amplitude. But instead of being displayed over here on a knob, it is being displayed down here on this right here, right? 200 millivolts per division, 500 millivolts per division. But guess what? Look at this. This VPP right here, it's measuring it automatically. And it's measuring that V peak to peak. It tells me exactly how many millivolts constantly. So much faster than what I was doing in there before, okay? You can also turn it on channel 2 here. See the other signal, turn channel 1 off, right? There again, VPP on this 100 millivolts right here. I can also see, what do I see here? The period, the frequency. I'm on 712 or 714 hertz right now. My VPP, 484 millivolts here at this point in time or whatnot. It's just the same, okay? I can change the time base here and tighten this up. And change the time base, and I can open it up. The difference is all these things that were a lot of buttons on the other unit. Look at this, AC coupling. What you do here, push the button tied to that. It's all menu driven. Then you push this button in. Now I'm DC coupled, okay? So if I have some DC offset on this unit, look at that. It varies the signal, right, as I change the DC offset. If I come over here and put this on AC coupling right here, click on it. Whoops, clicked on ground by accident. AC couple it, right? Now I am varying my DC offset, but what does it do? It always settles back down and it cuts out that AC component. I can limit the bandwidth of this unit if I want. I can tell it I'm using a 1X probe. Do you remember the other day? Hang on. We had plugged this unit in our differential probe, right? And look, times 50 or times 100. Watch this. I can come over here and say my probe. My probe happens to be on 50X, and I can click on that, right? And it'll change everything based upon that. Take it back to 1X, okay? So super smart little units. Lets you do, honestly, a lot of things that the unit I was showing you earlier can't do. I can invert my signal. I can limit the voltages. Over here on this side, I can measure period, I can measure frequency, I can measure rise time, I can measure fall time. I measure how long it takes the signal to go from here to here, how long it takes to go from here. I can measure the width of each signal. lots of measurement capabilities over here on the left just by clicking on this. Like right here, I can click frequency on channel 1 here. And all of a sudden right here, I'm measuring. This is a 712. Look at this. As I change the frequency, instantly this thing is measuring the frequency over here on the left and displaying that for me. Over here on the right, you've got trigger. Look at this. Remember before I would adjust the trigger and I didn't see a line. Here, it lets me see a line, exactly what I'm triggering on. So if I had something that alternated every other time and it was smaller the second time around, I can make sure I'm far enough down and it'll tell you the voltage level that it's actually triggering on here. Over here on the left, I can click on menu and I can say, hey, I want to measure voltage max or voltage this or voltage peak to peak, okay? As soon as I click on voltage peak to peak there, right there, now I'm measuring my voltage peak to peak. And as I vary that voltage, watch it. It'll read instantly what's going on over here. So these are just really smart units, but keep in mind, everything's kind of menu driven versus knob driven. So I actually think the learning curve is a little longer because you have to learn the various menu functions, and some of these are 2 or 3 or 4 steps deep in the menu. But once you learn it, remember I said this in my first video, what is the best oscilloscope you can own? The one that you learn. So if you get an oscilloscope, say you buy this Rigel and you learn everything about it, it is the best oscilloscope for you. I don't care what anybody tells you. Learn the oscilloscope you have, learn every function of it, learn how to work it for you, and it'll be your best friend. This one has a lot of stuff up here. It'll let you acquire signals and capture that picture and maybe measure it over the next 10 seconds and then play it back to you. There's just a lot of functionality in these. But at the end of the day, you can also use it very simplistically. Just put it on channel 1. Just vary the voltage, right? Volts per division. Change the time base, right? Use the position here. It's not rocket science, and it's very similar. And by the way, you can see my little trigger level right there. That little thing showing me on the side right there what my trigger level is at all times. Super simple, nothing crazy. One thing I do like about these little digital scopes, got a USB port on it. If you'll remember, on this unit, to get it to work, what did you have to do? You had to plug in a USB power cord. This provides you the USB power cord right on the front of it, ready to go. So if you're going to be using a differential probe, one of these is a nice way to go. Now, okay, just a few more things before I wrap this up. If you'll notice here, there's 2 ground lugs over here, 2 separate ones. One is tied here on the unit to basically, you could tie ground here and tie it back to something in your audio unit, and it would tie the internal ground sink on this to the audio unit. The other one here is actual chassis ground, and we'll talk about that a little bit more in video 4. When we actually get on the bench, hook this unit up, hook it up to, you know, a piece of audio gear with a dummy load and measure across the dummy load, things of that nature. So stay tuned on that. And I failed to mention on the previous oscilloscope, it had a banana jack that you could have plugged in and tied the ground of the oscilloscope down to the ground of whatever you wanted inside the audio unit. And if you'd used some kind of device to isolate the ground, then you could have kind of floated that ground and tied it to the oscilloscope. Next though, if you'll notice here, notice how this signal is a little bit jagged along the way. It's not perfectly smooth here, okay? That has to do with the resolution of the LCD screen. Now, you may say, well, gosh, that's kind of rough, and it looks super smooth on your other cathode ray tube based oscilloscope, Mark. Well, the reality is the cathode ray tube, it just takes longer for the fluorescence to fade out, so it always looks nice and smooth. So there's a smoothing factor that happens on a CRT based oscilloscope just from the fluorescence and how long it takes to go away. And this may be actually a little more accurate. However, there is the resolution of the LCD here that you actually have to deal with. So you may say, well, when do I use one of these versus the other? I actually like to use my 2246 on the bench a lot. I love it. It's simple to use. I love all the knobs. I don't have these deep menus I'm always hunting for and whatnot. So back to, it's the oscilloscope that I know well, so I use it all the time. However, anytime I'm not on my bench, I don't want to pick that big old 2246 up and carry it somewhere. If I'm working in here in the workshop area, or I'm going to a friend's house to test something out or whatnot, this is what I'd carry with me, and I love this unit. Nothing wrong with it. It's just not my day-to-day scope. I actually like the cathode ray tube based, but it's just what I grew up on and what I learned, so it's what I'm familiar with. And it's kind of like, you know, what's your favorite car? Well, it might be the one you know how to drive the best, you know, type thing, or favorite bike or motorcycle or whatnot. At any rate, hope you guys learned something. I had a lot of fun making this video. Part 4, we're going to get on the bench and actually use these things to actually test some stuff and get you thinking, how do I use my oscilloscope to solve audio problems, okay? Or how do I determine if I even have a problem with my audio on my unit via an oscilloscope? And then video 5, we're going to get into audio measurements via an oscilloscope and tell how good your audio signal is using nothing more than an oscilloscope. Thanks again for watching, everybody. Hope you're enjoying this series. If you got questions, ask them down below. I'll do my best to answer them. And let's all look forward to video 4 here in another week or so. Thanks, everybody.